Okay, so I should have done this video a while back, but I didn't know the explanations behind it were so terrible. I'm gonna try my best to give a decent explanation. So what I have here is a two variable function, f of xy is equal to x squared plus y squared, and we get a convex shape like this, right? And if you know gradient descent, if you don't know, it only works with, or it mostly works with convex functions. If you have a function, oh, sorry, let me paste that again. If you have a function that has multiple minimums, you won't be able to converge to your global minimum. And if you don't remember what a global minimum is, if you have some function like this, and if you start at this point, your global minimum is here. This is the lowest point in your function, right? And you want to input a value to get that value. You want to input a x and y value to get this point in your function, right? But gradient descent will actually have you. I'm gonna do this in blue. It will actually have you converge to here and stop. Or if you, for instance, start here, you're gonna go down and stop here. And I'm gonna explain why in a second. Instead of using a ball rolling down analogy, I'll actually explain it as well as I can. So the entire idea of gradient descent is to minimize your function. And what that means is I want to input an x, let's say a function f of x. I want to enter an x value into my function f that will give me the lowest possible result. And if not, but approximately the lowest possible result. And that's minimizing your function as opposed to maximizing. Now I'm going to explain um, how this is used in error functions in a second, but basically, if I start at some point in space here, I want to eventually input I want to input different x values over and over again until I converge to the lowest point in my function. Now I guess that's where you could use the ball rolling down analogy, but not to describe the entire idea of gradient descent. So let's start at some point here, and just pretend this is behind this wall, but I'm gonna define a new point. I'm gonna say x. I'm gonna say x sub 1 is equal to, and actually I'll use this. So x sub 1 is equal to x sub 0 subtracted by some step in the positive negative direction. I'm gonna explain what I mean by that in a second, and I'm gonna call this alpha, multiplied by and I'm gonna do this in this color, multiplied by your gradient of f, which is essentially derivatives, but I'll explain that also if you don't remember. So your gradient evaluated at x sub 0. So real fast, what I mean by gradient, that's going to be a vector of partial derivatives. And if you don't remember a multivariable function, we can't just derive all at once. So it's going to be the partial derivative of f with respect to x, and it's going to be the partial derivative of f with respect to y. So in this case, and I actually got this specific function from Khan Academy's video, and they explained it a little better in this section if you want to go check that out. So the partial derivative of f in this case is going to be 2x, so partial derivative of f with respect to x, and then partial derivative of f with respect to y is just going to be 2y. So from this information, you should be able to tell that as I input bigger points in space, so let's say I input this point right here, which appears to be 1, 1. Yeah, so 1, 1. Which means we're going to get the derivative of our point 1, 1 is going to be 2 times 1, 2 times 1. So we're going to have a vector in space pointing to 2, 2, right? Because 2 times 1 is 2 on both vectors. So this is our original vector, and our derivative function basically tells us to go here. So as we input higher points in space, we obviously increase in our function value because our gradient is increasing, right? These vector fields, if you don't remember what a vector field is, vector field it is a vector of every point evaluated at your function. So if I say take some point here in space and evaluate it with your gradient function, so I take this point and I plug it into my vector gradient function, then that is going to show me a vector field of that vector. Sorry if that's confusing, but you can always review what a vector field is. But essentially, this vector, and I'm going to do this in green, this vector is essentially a vector field, this specific one. Not this one, but that one. Because this is the vector of the point in space, and the green is the vector when I take that point in space and I evaluate it into my gradient function, right? So essentially this means that since the gradient points in the direction of the steepest ascent, that if I want to increase the value of my function, all I have to do is increase my bad. All I have to do is just continuously increase my x value, right? I just have to keep going in this direction. So if I just keep increasing the input that I enter into my function, I'll get a higher value, and that's maximizing. Now we want to do this the other way, and I'm gonna do this in I'll do this in pink. I want to go this way, right? I want to be able to actually decrease. So all I have to do is, instead of going up, I have to go a positive step in the negative direction, right? So I have to go this way, and that's essentially my goal. Now, you're probably wondering, why can't we just take x sub 0 and subtract it by a number and eventually get down to this point in our function? Now, the reason we can't do that is because this gradient, it acts as a control or a limit. I'm going to explain why in a second. So, actually, I'm going to explain it right now. So, our x sub 0, this point right here, I'm going to color this there. And this isn't accurate, obviously, but just pretend this is where our point is. And I'm going to subtract it by alpha, and let's call this 0.001. Just a small step. Actually, I'll do 0.01. So it's a small step. And this is my gradient evaluated at x sub 0, whatever that may be. This is just going to give some random value. And the reason is because we want to take a very small step, right? We don't want to take a very large step, because if we subtract x sub 0 by a very large number, we're going to end up somewhere here, right? So that's not what we want. We want to slowly go down. And again, this is somewhere where the ball rolling down analogy could be used decently. So we're taking this, and the gradient of x sub 0 is obviously going to be smaller than x sub 0 itself, right? And x sub 0 is not really accurate because this is two variables, but just stay with me here. Because if there's two variables, you're going to be subtracting two variables. But I'm just doing x sub 0 for this video. So we're taking a gradient, which is a smaller number, and we're multiplying it by a number that is less than 1. So there's going to be even a smaller number. So essentially, and let me erase this over here. Okay, maybe that wasn't the best idea. Let me just Control Z back. Okay, so essentially we're taking a very, very tiny step, but I'm going to make this a little larger just for showing. Let me do it in pink. So we're taking a very small step down our function. You can think of it this way, right? And we're ending up at our point x sub 1, right? Because if you think about it, x sub 0 minus a tiny small number, we're gonna end up, and actually, you know what? I'll just do it a very small number. We'll end up somewhere right here on our function. Now, what I mean by the gradient acts as a control is, I want you to imagine that our point is on this edge, because I can't really color inside here. So we'll just pretend that our point is on this edge. The gradient, right? So the slope, as we decrease in our function value, and I'm really trying my best to make this straight. Oh Lord. Okay, so as we decrease in our function value, then our slope is going to get smaller and smaller, right? And if I take this point, I'm going to have something like this, and eventually I'm going to get to this point where my derivative is just going to be 0, right? And this is a one-dimensional line, but you can imagine it like a plane hugging the third-dimensional function, right? So you can think of this as a third-dimensional, as a plane, right? I'm not going to draw that in actually, but as you can see, as we get to lower, and I'm going to do this in green, but as we get to lower and lower values in our function, our slope is clearly decreasing. So what does this mean for the calculation? It means that this value, the gradient of your x sub 0, is going to get smaller and smaller, and this is sort of a control, because at first we're subtracting it by 0.01 multiplied by a decently sized number. But as we get to, say, I'm going to do this in light blue, and I'm going to call this uh, this point right here, x sub 2, whatever. So as we approach x sub 2, our slope is going to get smaller and smaller, and it's going to get less than 1, right? Because think about it, these lines are going to keep, you know, not pointing as high, so our slope is going to decrease. So what I mean by this acts as a control is this is going to get smaller. So this might start at 2, then we'll go to 1.5, then we'll go to 0.7, 0.4, 0.2, right? As the input to our function decreases. And eventually, this flat line right here, if you don't remember, a flat line means your derivative is 0. Alright, so eventually we're going to be multiplying, but we're never going to actually approach 0. So I'm just going to say 0.000001. So now I'm multiplying my step. I'm multiplying a small step number by a very, very tiny derivative. So we can go, I can keep making these zeros, and which means x sub 0, and actually I'm gonna call this x2, right, is gonna not decrease at all, right? We're barely gonna decrease. If anything, we won't decrease at all at a certain point, right? And this is where the entire idea of gradient descent comes in, because we converge to this lowest point in our function and we stop. So we don't keep going up, we don't keep going that way, we just stop at that point. And again, if this is all confusing, just remember the entire point of minimizing your function is to input a value into your function that will give you the least result. And that's what we're doing here.